So before we summarize the substitution reactions together, let's talk about a couple of other factors that do have an important effect on these reactions. But later on, when we ask the question, what reaction's occurring, they're not going to have too much of an effect. But they do have an effect on the reactions themselves, but they're not really big on making the decision, is a reaction, say, Sn1 or Sn2. The first one is the leaving group itself. And if you look at it in both the Sn1 and Sn2 mechanism, the leaving group is removed during the rate determining step. So for Sn2, the incoming nucleophile pushes it off. In Sn1, the leaving group pops off during the first step. So it is involved in the rate determining step on both reactions. So the leaving group is important. Remember that the leaving group receives electrons in both of these reactions. That's the overall driving factor. And so the more that the leaving group is able to stabilize negative charges, the better leaving group it's going to be. And so this is going to be an important factor later on, that we're going to find that when we start talking about different types of leaving groups, that if the negative charge is not stable enough, that the species will not make a good leaving group. So that's later on. Right now, we are still focusing on halogens. So the only leaving group we've talked about is halogens, and they do stabilize negative charges quite well, mainly because of their electronegativity. So the thing you want to remember in the back of your head is that good leaving groups create stable negative charges. So the leaving group gains the lone pair electrons and the negative charge during this reaction, the substitution reactions. And the more stable that negative charge is, the better it's able to be a leaving group. So good leaving groups tend to be weak bases. This is something that they talk about quite a bit in books, and I don't really like to talk about it, but the one thing I want to point out is that we spent quite a bit of time talking about acidity. And with acidity, one of the things we wanted to look at is the how stable the negative charge is in the conjugate base. So we spent quite a bit of time talking about what's the most acidic hydrogen in a molecule. And what that came down to was how stable is the negative charge in the conjugate base. So it's kind of the same thing. We want to stabilize the negative charge. And so some of the ideas that we had with determining what's the most acidic hydrogen are going to apply to nucleophiles. So, or excuse me, to leaving groups. So the more stable the negative charge, the better the leaving group's going to be. And so for right now, don't worry about that so much because we're dealing with halogens. But later on, when we start looking at other types of leaving groups, this is going to be an important idea. So for right now, most leaving groups are halogens. And this is where it gets a little tricky, that halogens are electronegative. And remember, our trend for electronegativity is that as we go up and to the right, things get more electronegative. So if electronegativity was the only deciding factor on the stability of the negative charge, you would expect fluorine to be the best leaving group and iodine to be the worst. And actually, there's more to this story. The idea is that in terms of the electronegativity, larger halogens tend to be able to handle negative charges because of diffusion. They're more spread out. So when we talked about resonance spread out a negative charge between two species, like two oxygens. And because the negative charge was spread out, it was actually more stable. The same basic idea happens here, that a larger halogen means that negative charge is more spread out, and so it's more stable. So remember, the trend for ionic radius is as we go down into the left of the periodic table, we tend to get more larger. So electronegativity says as we go up, we get more electronegativity. Ionic radius says that as we go down, we become larger. And in fact, this larger trend tends to override electronegativity. So halogens tend to make good leaving groups because they are electronegative. But when we look at the relative ability of halogens to become leaving groups, it actually increases as we go down the column of the halogens. So we have chlorine, bromine, and iodine, and actually fluorine is such a poor leaving group that we don't consider that. So when we talk about all these reactions, we talk about leaving groups, you're never going to see fluorine inside of here. Typically what we use for leaving groups is chlorine, bromine, and iodine. And as we go down, we can see that bromine is 10 times faster or 10 times more able to be a leaving group than chlorine, and iodine's 100 times faster. So in between these, iodine makes the best leaving group. So reactions that involve iodine as the leaving group are actually 100 times faster than reactions that use chlorine as a leaving group. So leaving groups have an important effect, and the trend is as we go down the column, so fluorine would be up here, it's fluorine, chlorine, bromine, and iodine. As we go down, we tend to make better leaving groups, and this is because as we go down the column, we tend to make larger atoms. So iodine's larger than bromine, and bromine's larger than chlorine. So of the three, chlorine, bromine, and iodine is the best leaving group. So when I do substitution reactions, if I'm using an iodine as the leaving group, it's going to react much quicker. So good leaving groups tend to increase the rates of Sn1 and Sn2 reactions. So if I want to do a reaction, iodine leaving groups or molecules that contain iodine are actually going to work the fastest. But notice this is not going to help us make the decision of is my reaction Sn1 or Sn2? That's a completely different story. So the decision of what kind of reaction we're using is separate from how fast is this reaction occurring. So that's going to be something different. So we will talk about that idea, what reaction is occurring later on when we summarize all these things together. So another thing that's important is the nucleophile. And in Sn1 and Sn2 reactions, nucleophile kind of had a different role to play. So in an Sn2 mechanism, the nucleophile was involved in the rate determining step. So there's only one step in an Sn2 mechanism, so the first step must be the rate determining step. And in that mechanism, the nucleophile came in and directly pushed off the leaving group. So the nucleophile is involved in the rate determining step. So a good nucleophile is going to make Sn2 reactions better. And we'll summarize nucleophiles. But for right now, when I say a good nucleophile, I mean something with lone pair electrons and a negative charge. It's a good nucleophile. And if I have a good nucleophile, it tends to want to try to be an Sn2 type reaction because the nucleophile is involved in the rate determining step. So the exact opposite is true, that in an Sn1 mechanism, the nucleophile is not involved in the rate determining step. So in Sn1 reactions, what happens is the leaving group pops off. That's the first step. And then in the second step, the nucleophile comes in and attacks. So the rate determining step is the first one where the leaving group pops off. So the nucleophile doesn't come in until the second step. So the nucleophile is not involved in my rate determining step of an Sn1 reactions. So the idea is if I have a poor nucleophile, it's going to tend to favor Sn1 reactions. So what do we mean by that? Any molecule with a lone pair electron can act as a nucleophile, but there are good nucleophiles and poor nucleophiles. So anything with a set of lone pair electrons can act as a nucleophile under the right conditions. But what we're interested in is the difference between good nukes and poor nukes. And we will, when we push all these reactions together, I will give you a more defined summary. But for right now, when I say a good nucleophile, I mean something with lone pair electrons and a negative charge. And so a couple examples that we've already talked about is hydroxide and alkoxides. And so here, and I don't know why my negative charges are not showing up in here, this is hydroxide, so lone pair electrons on my oxygen and a negative charge, and alkoxide, so this is actually methoxide, lone pair electrons and a negative charge. That means it's a good nucleophile. And what we're going to find out is these tend to want to undergo Sn2 type reactions. Poor nucleophiles just mean I have a lone pair electron and no negative charge. So here's a new set of nucleophiles that we haven't talked about, water and alcohols. So water has lone pair electrons but no negative charge, and alcohol, so in this case it's methanol, but I could have just about any alcohol, ethanol, things like that. Alcohols have lone pair electrons and no negative charge, so they are poor nucleophiles. So these are two new nucleophiles that we really haven't talked about now. They have lone pair electrons and a neutral charge. And we kind of talked about that in the substitution reaction, that we tend to get these neutral nucleophiles. And remember, we had a separate mechanism where the neutral nucleophiles lose a hydrogen. That comes about when we're doing an Sn1 mechanism, because Sn1 mechanisms tend to use neutral nucleophiles. We tend to get an extra step inside of there. So one important exception is amines. Amines are a neutral nucleophile that are actually a good nucleophile. Don't worry about this. We're going to talk about amines in a separate portion of this class, and we will talk about their ability to be a nucleophile. But just know right now, amines are a major exception to this idea I just gave you. Amines are neutral, and they are a good nucleophile. So just remember that now, but we will come through and talk about amines separately. So one other thing you want to understand, I'm going to introduce this to you, and we will come back through and talk about it a little bit more. They are sometimes we can force a reaction to do something that we want by changing the actual nucleophile itself. So the idea is it's called a big bulky group on a nucleophile, and it's also called a big bulky base. So I'm going to introduce it to you now, and then we'll come back later and see it in actual use. But I'm introducing to you guys this molecule called T-butoxide, and it is an alkoxide. So remember, an alkoxide is a deprotonated alcohol, lone pair electrons around, so there's 3 sets of lone pair electrons and a negative charge. That's an alkoxide. T-butoxide is a specific type, and here it's got these big bulky groups. So when we compare T-butoxide and methoxide, T-butoxide has a lot more sterics to it. By sterics, I just mean there's a larger group. And this is going to have an effect on our reactions, and we're going to exploit this to cause a specific reaction to occur. And we'll talk about that later, but just remember that when I talk about a big bulky base, we're talking about T-butoxide, and the difference between T-butoxide and other alkoxides is that T-butoxide is sterically hindered. By that I mean it has a big group around it, so it's kind of hard to get things in next to the oxygen part. So we will see that in action a little bit later.